Okay, so today we're going to cover Bode plots. Is a representation of frequency response of a system, and this has many applications in control systems, in electronics. It's basically a picture that represents how the system responds to a given frequency excitation at various frequencies. And it carries a lot of information. One main application of Bode plots is that by taking the Bode plot of a system, if you can define that experimentally, we can infer the transfer function of the system just based on the Bode plots. There's a lot of real applications of this. And when, for example, you buy a component for your electronic system or for a mechanical system, you're probably interested in looking at the Bode plot to see at up to which frequency that a specific component is recommended. Okay. When you buy any electronic components, you'll see a Bode plot of that component there. So we'll see how to read and how to create one. So from experience, I think that this is one of the topics that is students struggle the most. So you might require a bit extra practice to really grasp the content. So today we're going to look at real poles and real zeros, and then in lecture 16, we're going to include complex poles and zeros and the concept of resonance frequencies. So let's get started with the simpler version of a Bode plot. That is Bode plots for transfer functions with real poles and zeros only. So today, the objective is to understand the concept of Bode plot, how to read one, how to draw one, and represent the magnitude and phase of a transfer function in a Bode plot. We saw this in the last lecture, so let's just do a quick recap here. A frequency response of a system tells us how the transfer function of that system is. And if you take a linear time invariant system G of S and you apply a sinusoidal input to it, we get a sinusoidal input in the output. And this sinusoidal input in the output will have a different magnitude than the input, and that magnitude shift will depend on the magnitude of G of S at that frequency. It will also be shifted in time with respect to the input, and that a shift will depend on the phase of the function G of S. So if you apply a signal, a sinusoidal input to the system, the output will also be a sinusoidal, and here is the expression for the output. We have A as the magnitude of the input at a given frequency omega 0, and the magnitude of the output will be A times M, and M is a scaling factor, and this scaling factor is nothing else than the magnitude of the transfer function at that specific frequency. We calculate the magnitude of the transfer function by taking the square root of the real part of the transfer function squared plus the imaginary part of the transfer function squared at the frequency we are evaluating the system at. We also notice that there is now a phase shift, and this phase shift can also be calculated based on the transfer function, and we can simply calculate that based on the angle of the transfer function, that is the inverse tangent of the imaginary divided by the real part at that specific frequency. Okay, both parts are frequency dependent. We used this example here to determine the frequency response at one specific frequency in the last lecture, and I believe that frequency was 0.5 seconds. So we applied a sinusoidal waveform of magnitude 1 at 0.5 radians per second, and we determined the output of that system. Now let's assume that instead of just evaluating the system at one frequency, we want to see how the system behaves at a variety of frequencies or a larger range of frequencies. In that case, all we have to do is to, instead of replacing the frequency with j omega, with 0.5, we just replace that with the j omega, and then evaluate the whole thing at a range of frequencies omega. So to do that, we find the transfer function between the input and the output. Here it is. That's from the last lecture. We can now get rid of the j in the denominator once we replace s with the j omega by multiplying the equation by j over j. And here we have the final format of this transfer function, 2 minus 1 over omega j. The real part is 2, the imaginary part is 1 over omega. If you want to evaluate real square root of real plus imaginary part squared, and the phase of the transfer function is the imaginary divided by the real part. Now notice that both of these, both the phase and the magnitude, are functions of the frequency. As you change the frequency input, the phase and the magnitude will now change. So the ratio between the input and the output is frequency dependent. The phase shift between the output and the input is also frequency dependent. So this is the same we did in the last lecture. It's just that now, instead of just looking at 0.5 radians per second, we look at a range of frequencies. And you can very well just change this frequency and plot the results. And this is what we get. So here we have a range of frequencies that is going from something close to 0 to 10 radians per second. And the top graph shows the magnitude of this transfer function. The bottom shows the phase of the transfer function in degrees. Excuse me, what can we see here? We can see that the phase changes from negative 90 to 0, and the magnitude of the transfer function decreases sharply towards 0. So this is something that is getting close to being a Bode plot, except that the units here are not the same as in a Bode plot. If you look at the frequency, when you plot the results, all the information is concentrated in this portion here. Everything else is the same. Right? And same with the phase. We have a phase shift that occurs here, and then everything else is pretty much the same. So instead of plotting the results like this, to highlight these changes, we are going to use a different scale. I'm going to use a log scale for that. And the reason, again, is that it's easier to see these changes in a log scale than it is in a regular scale. So this is what we would get in a regular scale by, again, simply changing the frequency and plotting the magnitude and phase. And this is what we get if you use a log scale. So now, both on the on the y and the x-axis, we have a log scale of this magnitude. So instead of taking simply magnitude of gj omega, we are taking log 10 of that and displaying the results here. And you can see now that the change is kind of spreads out a bit, and it's easier to see what the changes in the transfer function magnitude are. The phase that is still in degrees. So you notice here that we didn't change the phase scale, it's still in degrees, but the x-axis is also now in log scale. So these numbers that we see now here are in fact the powers of 10. All right, so at this point here, we have 10 radians per second. At this point here, we have 10 to the power of 0 is 1 radians per second. And anything below that is, for example, 0.1 and 0.001 radians per second. So the phase is in a log scale, and also the frequency axis is in a log scale, just to highlight these differences. The phase itself remains in degrees. That doesn't change. Okay. Any questions up to here? We good?
Yep.
Yeah, all right. So there's another complication, little complication that we are going to use here, is that for the magnitude, you're going to express the magnitude in a specific unit called the decibels. And this comes from when the telephone was invented. They wanted to check what was the minimum detectable change in magnitude that it would result in a noticeable change in volume, and it turned out to be the decibel. And it's kind of an arbitrary unit that we use now, but it comes from that era. Simply, instead of plotting log 10 of gj omega, we are going to look at 20 log of 10 gj omega, and one unit of that is called 1 decibel. So if you take a point in this scale, for example, here, 9 decibels, what is the actual magnitude of the transfer function? Well, that was taken by calculating 20 log of the magnitude of gj omega, and that was 9, same as log the magnitude of gj omega equals to 9, sorry, that's 20, I wrote 10 for some reason. No, sorry, I was right, it's just my L, okay, that's it. 9 divided by 20. All right. And now if you take the, you put everything to the power of 10, 10 log of power of 10 is 1. So this is the same as gj omega. The magnitude of it is 10 to the power of 9 over 20. And that's the actual magnitude of the transfer function, but you're now taking the log 10 of that, multiplying by 20, and then we display the magnitude in decibels there. And again, the frequency is also in a log scale, so these numbers that we see there are all powers of 10. Okay. Now the unit of our transfer function gain, that's what we call the top graph, the magnitude or the gain. Why gain? Because that's the amplification ratio between the input and the output. That's given in decibels. Right? Phase is given in degrees and the frequency in radians per second. Let's give an example here what we can see exactly in a Bode plot. Let's consider this example here, where we have a muscle that is subjected to a sinusoidal input force. And this sinusoidal input force has a magnitude of A and a frequency that will change over time. What would be the ratio between the input and output if we plot this ratio over a range of frequencies? So let's create an equivalent model here that will make the problem a bit easier to understand. So this is a muscle subjected to a sinusoidal excitation. But we could see that if the muscle is just modeled as having a damping ratio of B, sorry, a viscous friction coefficient B, and it has an inertia due to the mass, we can say this is the same as having a mass sliding over a plane with the viscous friction coefficient B. And then we can have a little motor here that is applying a displacement to this mass that it goes back and forth like that. It's the same as the other one we have there. So this, it would be a force applied to the mass that slides on a plane with the viscous friction coefficient B. And when we change the force input frequency, we are basically switching directions, faster or slower, depending on the frequency. Now let's see what happens to the speed. If we start with a very low frequency and let the system run, so it's going to apply a force one way for some amount of time, then the other way, and then back and forth. And then you're going to slowly increase that frequency and see how the system behaves. You would agree with me that if we let the system run indefinitely, the speed would reach a finite steady state value. Is that clear? If we just turn the system on and apply a constant force to it, the final speed, the final value of the speed is a constant value. It doesn't tend to infinity, right? Yeah?
Yes.
Yeah. So if we apply a low, giving the system enough time to reach a steady state means that the frequency we are applying to the force is very low. So let's say you let the system go one way 10 seconds, and then it goes the other way another 10 seconds, which is the same as giving the system enough time to reach a steady state. So at a given low frequency, the system would reach a maximum speed. And now we can plot here the ratio between the magnitude of the force and the speed. It's there. And now if you increase the frequency slightly, well, the system will still reach that same maximum speed. And you can keep going up to a certain point. This maximum speed doesn't change, provided that we give the system enough time to reach a steady state, one way and the other. The maximum speed it reaches is the same. So the ratio between force and speed is constant. Where now, if we do that too fast, inertia comes in the way. And now the system doesn't really have time to reach this steady state value. And the faster you switch directions, the the lower the maximum speed becomes. The faster you switch directions, the lower the maximum speed becomes. You can try that with your arm. If you go at 1 hertz, you see they can reach a steady state speed. If you go at 2 hertz, you see you can still reach that same steady state speed. But now if you go too fast, you don't have time to develop that full speed, and the ratio now between the amount of force you put in and the final speed starts to decrease. So this eventually starts to decrease. And this ratio now drops as the frequency increases. And this point here where the system starts to change change magnitude, we're going to call that the cutoff frequency, which depends on the mass and on the viscous friction coefficient of this particular system, right? And then past that point, this ratio decreases. And this is what you can see in the Bode plot. Is this clear?
Yeah, just
Yes.
here. Yeah. Professor, you write the F over V. So what's the relationship between the F over V and C over A?
It should be C. So the output, yeah, sorry, this is a flip. This is the output divided by the input. So V over C, yeah.
Okay.
Or it would have to go.
Okay, thank you.
Sorry, V C over speed divided by force. Now force is the same, and then the speed, the maximum speed starts to decrease. Now let's think about the same problem, but in terms of position. Let's assume now that we have the same as before, but now instead of looking at the final speed, we are looking at the final position. And now we're going to look at the ratio between the final position it reaches and the input force. How would this look like? How would this look like? Would it also be a flat line in the beginning? Now this is likely, yes, go ahead.
Would it have the opposite relationship?
It would have the opposite relation. Well, not really, because then it would mean that the less time we give to the system, the higher the final speed, the final position, right? So let's think about it. If we give a system, let's say 1 second to run one way, it will reach, say, 1 meter. And if you give 2 seconds, then it goes to 2 meters. If you do 3 seconds, it keeps going up. If we now start to decrease the time we give to it, that is, the frequency is decreasing because you're switching directions faster, the position it reaches becomes smaller and smaller. So we actually should see something already decreasing over time like that. Right? When you go to the left, this means that the frequency is decreasing. The system is running, is changing directions at a lower frequency, so it has more time to move one way and move the other way. And as we increase the frequency, then we are changing that faster and faster, and the maximum displacement decreases. So we should see something that immediately decreases like that. And once we reach that same cutoff frequency we saw before, then we have this slope decreasing faster, because now we reach the point where inertia and friction become a problem in the system. Right? And this is again the cutoff frequency we saw before. Right? And this information can be seen in the Bode plot. If you do all the entire procedure we just saw, we should see something like that.
Professor,
does it make sense?
Professor, do you mind going over the speed Bode plot again, please?
Yeah, so the only difference with the speed is that this line here is going to be flat. And why is that going to be flat? Because if you let the system run for 1 second, or 10 seconds, or 100 seconds, the maximum speed it reaches is the same. It doesn't keep accelerating forever. It's a finite value for the speed. Whereas here, the more time you give to it, the farther it travels. So that's why it goes up.
Well, why does the speed remain constant?
Well, if you apply a force to a mass spring to something like this, and apply a force F, you reach a steady state value that is the magnitude of force divided by B in a steady state.
Oh, okay, thank you.
Okay, so this information can now be seen on the Bode plot. So let's see how exactly we can calculate these things for more complex systems. This one is intuitive, is easy to find, but let's look at something based on the transfer function. So if you have a generic transfer function as a ratio of multiplication of poles and zeros times a gain, we are now taking the magnitude of this transfer function, and we are doing that in a log scale. So that is, we are taking 20 log of this magnitude. And remember that a log of A times B is the same as log A plus log B. And log A over B is log A minus log B. Which means that we can rewrite this entire expression as now 20 log of K, this is a gain here, minus the sum of the magnitude of each zero plus the sum of the magnitude of each pole. And we have very important conclusion here is that if we now can define the Bode plot for individual poles and the individual zeros, all we have to do to find the Bode plot of the entire transfer function is to add them up. So if you know the Bode plot of basic functions, we can sketch the Bode plot of the entire transfer function. So all we need is the Bode plot for gains, constant gains, zeros, and poles. And if you have those, if a transfer function has many of these, just add them up, and that's the Bode plot of the entire transfer function. Now let's look at the phase. The phase is similar. We are not using the log scale for the phase, but we saw in the last lecture that if we have a transfer function that has poles and zeros, the gain of the transfer function is the sum of the angles of all zeros minus the sum of the angle of all poles. Right? This is the same as minus the sum of I equals to 1 to m of the angle of poles. Okay. Again, now if we have multiple poles and zeros, just find the phase of each of these elements individually, add them up to find the phase of the entire transfer function. So all we need to know is this building blocks for a Bode plot. And let's start with the simplest one. The simplest one is a constant gain. Constant gain means that the transfer function is simply g of s equals to k. If you want to find the magnitude of that, oh, that's easy. It's just 20 log of k. And you notice that this is the same for all frequencies. It's frequency independent. To find the phase, we can do inverse tangent of imaginary part divided by real. Imaginary part is 0, real part is k, and this is 0. So the phase is always 0. We can also see that if we plot this on the imaginary real axis. So if the gain is just k, we have k going here. This is the magnitude, is this distance. And the angle we formed with the real axis is 0. So the angle is 0. If we have a magnitude of negative k, then it would be sitting over there. The magnitude is still the same. The magnitude is a positive number always. This is still k, but now the angle becomes 180 degrees. Right? So for a constant gain, we have a magnitude that is 20 log of that gain for all frequencies, and a phase of 0, or negative 180 degrees if the gain is negative. So on the Bode plot, that is simply a horizontal line for the gain for all frequencies and a horizontal line for the phase for all frequencies. Okay. Now let's look at the second building block. We have a pole located at the origin. And in this case, g of s is simply 1 over s. We can do Now to find the magnitude, replace S with the j omega. This becomes 1 over j omega. And I'll take 20 log of that. Yeah. This would be the same as 20 log of 1. Sorry, the magnitude here only takes omega. J indicates the imaginary part. Minus 20 log of omega. This is 0. Now the magnitude becomes negative 20 log of omega. Notice here that every time we multiply omega by a factor of 10, the magnitude goes down by 20 decibels. For example, in a frequency of 1 radians per second, what is the magnitude? It's 20 log of 1, which is 0. At a frequency of 10, we have negative 20 log of 10. Log of 10 is 1. We have negative 20. At 100 radians per second, negative 20 log of 100. Log of 100 is 2. Negative 40. And so on. As the frequency increases by a factor of 10, the magnitude of the Bode plot decreases by a factor of 20 decibels. This increase by a factor of 10 in frequency, we are going to call that a decade. One decade in frequency results in a phase, in a magnitude decrease of 10 decibels. So we can say, for example, here that a constant or a pole at the origin results in a decay of negative 20 decibels per frequency decade. Again, when the frequency increases by a factor of 10, magnitude decreases by a factor of negative 20. Now let's look at the phase. The phase is the inverse tangent of the imaginary part divided by the real part. And that will be negative 90 degrees. If we take the expression 1 over j omega, multiply that by j over j, this gives j, negative j over 1, negative j times 1 over omega. So you see the real part is 0 and the imaginary part is negative 1 over omega. So this angle is always 90 degrees for all frequencies. So here we have the phase of a constant of a pole at the origin. Magnitude decreases by a factor of 20 degrees per decade, and the phase is always negative 90 degrees. Are there any questions? No? Are you sure?
Professor, what did you say about the slope again? You said it was negative 20 decay?
Negative 20 decibels per frequency decade. So if you look here, for example, when we are at a frequency of 10 to the power of 0, which is 1 radians per second, the magnitude of the transfer function is 0. When you go to 10 to the power of 1, which is 10 radians per second, notice that the magnitude is now negative 20. So what happened? We move in the frequency by a factor of 10, by 1 decade. The magnitude went down by 20 dB. So the slope is 20 dB per decade, negative 20 dB per decade.
Professor, could you please explain the phase one again?
Yeah, so the function we are dealing with is 1 over j omega. Right, 1 over s is j omega. Multiply this by j and by j, we are left with negative 1 over omega j plus 0. Now this is the real part. This is the imaginary part. We can now plot it. It will be sitting, oops, right here, 1 over omega. This is the imaginary, this is the real. This is the magnitude, and this is the phase. And you see that the phase is always negative 90 degrees.
Okay, got it. Thank you.
Yeah, for all frequencies. So now let's do a zero at the origin. The zero at the origin, you just have a transfer function g of s equals to s. And now we can do the same process we did before, and you'll find exactly the opposite as the pole. Notice that now we are dealing with 20 log of omega. Before we had 20 log of 1 over omega, which was negative, the same as 20 log of omega. We have a real part now that is simply omega, now 1 over omega is shown here. Let me just clean this up. If you look at the real and imaginary part of this transfer function, now the transfer function is simply j omega. So here is the imaginary part. Real part is still 0. If you plot that, we see that we now are on the positive imaginary axis. The angle is now plus 90 degrees. Right. So let's recap. For the pole, we had negative 20 log of omega, and that resulted in a slope of negative 20 decibels per decade. Now we have plus 20 log of omega. So it's the same, but another slope goes up. So if you change the frequency by a 1 decade, increase the frequency by a factor of 10, the magnitude goes up by a factor of 20. And the phase is plus 90 degrees instead of negative 90 degrees. Okay, is the opposite as the pole. You see here it goes down, here it goes up by the same amount. We can now consider the case with the multiple poles and the multiple zeros at the origin. And this is relatively simple. The only thing that it changes is the slope and how many degrees the phase shifts. If we have now a system with a degree of, let's say, n, so g of s equals to j omega to the power of n. This is 20 log of omega to the power of n. And because of the log property, we can write n times 20 log of omega. This means now that we have the same as a pole or a zero multiplied by the degree of that function. So if we have 2 poles at the origin, the slope will be 40 decibels per decade. If we had 3 poles at the origin, the slope would be negative 60 dB per decade, and so on. If we have 4 zeros at the origin, what is the slope?
80.
What is the slope? Plus 80 decibels per decade. And for the phase, same thing will happen. We just multiply the degree by 90 or negative 90. So for each pole, we have a phase shift of negative 90 degrees. So 2 poles would result in a phase shift of negative 180 degrees. And for every 0, we have a phase shift of plus 90 degrees. Okay. And again, they all reach 0 gain at 1 radians per second. Right? 20 log of omega, or 20 log, or negative 20 log of omega, when omega is 1, is 0. So they all meet at the same point here, and they have different slopes depending on the degree. Okay, so this is the first 3 building blocks. These are the first 3 building blocks that we need to build Bode plots. Now let's see how we combine them. Let's do this exercise. It's a very simple exercise. Sketch the Bode plot for the function 10 over s. Function 10 over s, what is the Bode plot? So the first thing to do here is to find these building blocks. Which building blocks can we identify here?
There's a pole.
There's a pole at the origin. Yeah, there's a pole at the origin. What else?
There's a constant gain.
And there's a constant gain. Very well. So here is the Bode plot. Let me see. Yeah. And with function g of s equals to 10 over s. So we saw that because they have two building blocks, we can do the Bode plot for each of them and then simply add them up. So let's start with the constant gain. See the constant gain, constant 10. What happens to the constant 10 in the Bode plot? Oh, we are doing that in decibels, don't forget. So you're taking 20 log of 10. And this is equal to log 10 of 10 is 1. That's equal to 20 dB, decibels. And this is for all frequencies. So on the Bode plot, this simply gives this is going to be a nightmare to draw here. This is going to be a constant gain of 20 dB. Well, this is for the constant 10. And what is the phase for that constant? Is 0, right? 0 will just follow a straight line along 0 here. I'm not even going to bother with that. The second building block is 1 over S. And for 1 over S, which is the same as 1 over j omega, which is the same as negative 1 over omega j. What do we do? Well, this is a pole at the origin. And the pole at the origin has a slope that it decreases by a factor of 20 decibels per decade as the frequency increases by a factor of 10. So this is now frequency dependent. So the first thing to do here is to define our frequency range. So let's just start here by specifying this frequency to be 10 to the power of 0. That is 1 radius per second. 10 to the power of 0. This one here will be 10 to the power of 1. And this one over there will be 10 to the power of negative 1. 0.1, 1 and 10 radians per second. Now this thing will create a slope that decreases as the frequency increases. And we know that at 1 radians per second, it will be 0 because again, we are dealing with 20 log of 1 over omega, which is the same as negative 20 log of omega, and negative 20 log of 1 is 0. So this function will, and this is the case for all poles and zeros at the origin, they will always pass through 0 dB at 1 radians per second. So this thing, it has a slope of negative 20 decibels per decade. If you now go to the frequency of 10, this would be negative 20. If you go to the frequency of 100, it is going to be negative 40. So what is the magnitude here at 10? Is negative 20 log of 10. That's negative 20. It's right there, negative 20. And what is the magnitude at 10 to the power of negative 1? If here we are 0, now we're going backwards. We are decreasing the frequency by a factor of 10. What is the magnitude at 10 to the power of negative 1?
20.
20. Exactly. So that's 20. It's right there. And this becomes now on that. And this is for 1 over S. Okay. So now we have these two. What do we do? Because you're dealing with a log scale, we can simply add them up. So when you add these two up, what happens? Well, this curve just shifts upwards by a factor of 20. So here we have 0 plus 20, that's 20. Here we have 20 plus 20, that is 40. And here we have negative 20 plus 20, that's 0. All right, so this now goes like that. Okay, here it's not. There we go. And this is the function 10 over s. Okay. What happens to the phase? Well, the phase is the phase of the constant, that's 0, plus the phase of the pole at the origin. The pole at the origin has a phase that is negative 90 degrees, always, for all frequencies. So this is just a constant line at negative 90 degrees. Are we good? Any questions here? This is the final Bode plot. Any questions here?
Sorry, for the phase angle, you said that you added them?
Yes, I added 0 from the constant gain and negative 90 for the pole at the origin.
Perfect, thank you.
Professor, I'm still a little bit confused about the phase because in previous slides, it's the n multiplied by the 90 degree. So,
yeah, so n in this case is 1.
Oh, yeah,
right?
it is 1. I'm sorry.
Yeah.
My bad. Got it. Thank you.
Other questions? Yeah.
Yeah, the plot for 10 over s from 1 over s, like what did you do?
Sorry, which the 1 over s?
In red, how did you get it from the plot in yellow, the 1 over s?
The 1 over s is this one, right? Is this line. This line is the 10. Right? So when we multiply them with 10 over s, that is the same in log scale as this plus that.
Okay.
Right? So by just adding these two in a log scale, that is the same as multiplying them as in a non-log scale.
Oh, okay. Okay, thank you.
I remember that log of AB equals to log A plus log B. Right, so here I added these two, I did log A plus log B, which is the same as multiplying 10 and 1 over s in a non-log scale. So what would happen if this was 10 to the power of s, 10 divided by s squared? What would be the result?
The slope would be greater.
The slope would be greater, exactly. So this would now be greater, and it would be at this point, instead of 40, it would be how much? It would be 60, right? And in this point here, instead of 0, it would be negative 20. Yeah, right? Because this one is shifting. So if we forget about the 10, this instead of negative 20 would be 40. And this instead of negative 20, it would be negative 40, because you're now dealing with two poles. So instead of plus negative 20, we have plus minus 40 for each decade. So this basically just shifts like that. And then we move everything up by a factor of 10, because it's still multiplied by 10. So instead of 40, we would have 60. Instead of negative 20, we would have negative 40.
For
What would
the
have,
sorry,
go ahead.
For the 10 over s, like why did you why does it go up by 20 for each point, not 10?
The 10, so the 1 over s, if you decrease the frequency by 10, it goes up 20. If you increase the frequency by 10, it goes down 20.
Oh, yes, from before. Okay.
All right. If you do 1 over s squared, you decrease by 10, it goes up 40. Increase by 10, it goes down 40. And then everything is shifted up 10 because of this guy here on top.
Everything shifted up by 10 because of that. So the one.
What would happen if this was instead 10 times s?
So it'd be a 0 instead, not a pole.
Would be a 0 instead of a pole. So for the also for the 10 over s squared, the phase would now be negative 100, negative 90 for each pole. If you have 10 over s, what happens? Well, 10 doesn't change, it's still a constant gain. But now for a 0, the slope inverts. Right? And now this curve would go like that. I would start at -20, passing by 0, going to 20 because of the S, and then everything would go up 10, not 20 because of 10.
Okay.
Okay. And then the phase would be positive 90 degrees.
Okay, thank you.
Any other questions? Any other questions? So I know that this is it's a lot of information there, and this is can be a bit tricky. So let me know if you have any questions. And address them now before we move on, because this is getting a bit more complicated. No good. All right.
Sorry, just going back to what you said before about if we had a S squared term in the denominator, wouldn't it still start at 0, but just decay to -8 or -60?
Yeah.
Instead of starting at 40?
It would go to, if you only had 1 over S squared, here would be 0, and here would be -40.
Yes.
Yeah, but then if you multiply everything by 10, everything shifts up by 20.
Okay.
Right, so
Yeah,
then
that
instead
makes
of
sense.
negative,
I must have misheard you when you were originally explaining it. Thank you.
right, 1 is for 1 over S squared, then it would be indeed -40. 10 over S squared would be -20. Because it just shifts up. And what happens if this was here 10 over, let's say 100 over S?
The upward shift would just be greater.
The upward shift would be 20 log of 100, which is the same as 20 log of 10 squared. The 2 comes to the front. That's 40 log of 10. That's 40. So everything would shift up by an additional 20 decibels. It's already shifted up by 20. Multiply this by 2. It's another 20. Moving everything up. Okay, so now let's complicate things a bit. So this is real for the real poles and the real zeros. Now let's see what happens if you have a at the origin. And let's see now what happens if they are not at the origin, they are somewhere else. Like in the example we saw for that muscle with a, what do you call the cutoff frequency at some point. Let me just erase this and then I'm gonna do that so it's ready for the next exercise. Okay, this is the next topic now. Is when you have poles on the real axis. Instead of the origin, they're somewhere in the real axis. In this case, we would write the transfer function as ω0 times S plus ω0. And when you divide everything by ω0, we have 1 over S ω0 plus 1. And this ω0 is what we're going to call the cutoff frequency. Is the frequency from which the Bode plot will start to decrease. Okay, so that's the standard form of our function now. So ω0 is a constant that depends, a fixed frequency that depends on the characteristics of the system. And S is still j omega. So omega is the frequency we are changing. ω0 is a constant. And by replacing S with the j omega, this is what we get. Now to get rid of the complex variable in the denominator, as we did in the last lecture, just multiply the function itself by its complex conjugate. And here we have the expression now that highlights the real and the imaginary part of the transfer. With that, it's easier to calculate the magnitude. You just take the square root of a real plus imaginary squared. And you can go through the derivation here, but it's just simple math. You can do that for practice later. It's a good exercise, but just to give you the final result. When you take the square root of the real plus the square root of the real, the square root of the real part squared plus the imaginary part squared, here's what we get in the result. Square root of 1 over omega squared divided by omega 0 squared plus 1. Again, omega 0 squared is the cutoff frequency, is a constant, but it depends on the system characteristics. And omega is the frequency we are changing to do the Bode plot. If we want to calculate the magnitude now in decibels, just take 20 log of that. And 20 log of that will allow us to rewrite again with the very simple math. You can check these steps later as follows: negative 20 log of the square root of omega divided by omega 0 squared plus 1. And if you want to do the phase, just to go back one step, take the inverse tangent of the imaginary divided by the real part. That's what we are doing here. And this is the final result. I'm going to skip all the derivation, but this is what we should get. The procedure is the same. Find the real and the imaginary part, take the square root of the square, do the inverse tangent from the imaginary divided by real. These are the two we get. Now let's analyze each of them individually. Let's start with the magnitude first. And now we have to distinguish three different cases. The first case is when we are evaluating the system at a frequency that is much lower than the cutoff frequency. So in this case, omega is much smaller than omega 0, which means that this first term here tends to 0. And we are left with simply 1 in the square root. Negative 20 log of 1 is 0. So if the frequency of your evaluating the system at is much smaller than the cutoff frequency, the gain tends to 0. We can do the same with the phase. And in that case, we have 0 divided by something that's the arctangent of 0, which is also 0 dB. So up to the cutoff frequency, before we are increasing the frequency slowly, up to the point where we meet the cutoff frequency, we can say that the gain is 0 and the phase is also 0. Then we reach the point where we actually meet the cutoff frequency. In this case, case number 2, the frequency we are evaluating the system at is exactly omega 0. So this division here becomes 1, and we are left with negative 20 log of square root of 2, which is negative 3 dB. And if you take this as 1, if you take inverse tangent of that, that is negative 45 degrees. So at the cutoff frequency, the gain is negative 3 dB. The phase is negative 45 degrees. The third case is now the opposite. Now the frequency we are evaluating the system at is much greater than the cutoff frequency. So this term will be much greater than 1, and we can neglect that number 1. And if we do that, what we are left with? We are left with negative 20 log of square root of omega squared divided by omega 0 squared, which is negative 20 log of omega squared divided by omega divided by omega 0. Okay. And the phase is now the opposite, is the phase of a very large number, and that is negative 9 degrees. So let's see again what we have here. If we're now evaluating the system at a frequency that is 10 times greater than the cutoff frequency, omega equals to, let's say, 10 omega 0. What is the magnitude? Is 20 log of 10 omega 0 divided by the omega 0. That's negative 20 log of negative 20. If you do a frequency that is 100 times greater than omega 0, we get negative 40. If you get a frequency that is 1,000 times greater than omega 0, we get negative 60. What do we see here? The same trend as before. For every shift in frequency by a factor of 10, the Bode plot decreases by a factor of 20 with respect to the cutoff frequency. Let me summarize all this. Case 1, up to the cutoff frequency that I'm highlighting here as omega 0, the gain is 0. At the cutoff frequency, that's case number 2, we are at negative 3 dB. And past the cutoff frequency, the magnitude of the Bode plot decreases by a factor of 20 decibels as the frequency increases by 1 decade from this point. So if we are at omega 0, we are at negative 3 dB. At 10 times omega 0, we should be down by negative 20. At 1,000, we should be down by negative 60, and so on. So as the frequency now increases by a factor of 20, the Bode plot goes down by a factor of 10. The Bode plot goes down by a factor of 20. Okay. It's the same as we saw before, same type of slope, but notice that now the slope starts to decrease at the cutoff frequency. And as the cutoff frequency is as the frequency increases by a factor of 10 with respect to the cutoff frequency, then we start to go down by negative 20. The phase has also 3 distinct phases. The first one is at 0. So up to the cutoff frequency, the phase is 0. At the cutoff frequency, we go to negative 45. And past the cutoff frequency, we go to negative 90. So the phase should do something like this. In reality, it's going to be a more smooth function, passing by negative 45 degrees at the cutoff frequency. Okay. So let's assume, for example, that in this case, the cutoff frequency was 10 radians per second. What would be the magnitude of the transfer function at 100 radians per second? What would be the cutoff frequency is 10? What is the magnitude at 100? That is a factor of 10 in the frequency. So the magnitude goes down by negative 20. So what is the magnitude at 100? Is negative 20. Right? If you want to include the negative 3, then it would be negative 23. Right? But forgetting about the negative 3, it would be 0 at 10 radians per second. It would be negative 20 at 100 radians per second. It would be negative 40 at 1,000 radians per second, and so on. Now this shift, it starts at the cutoff frequency, not necessarily at 0 as we saw before. Any questions here?
No.
No? All good? We'll do an exercise, maybe that will help. Here is the exercise. No questions here. We can move on. Yeah? Okay. So let's do one exercise. So here we have that example we considered for the muscle that was modeled as a mass damper system. Sketch the Bode plot corresponds to ratio, the speed force ratio of a mass of 1 kilogram and a coefficient of viscous friction of 0.1 Newton second per meter. So let's do this. She starts here and then we go to the whiteboard. So you're applying a force to the system. The muscle is simply a viscous, it has a viscous damping in it. And we want to calculate the Bode plot as the ratio between the force we apply to it and the output speed. To do that, we need to find a transfer function. A transfer function, in this case, we can find that from the equation of motion. Here is the free body diagram, only two forces acting on it, the force we apply and the viscous friction in the system. So we can do the sum of all forces equals to m times acceleration, which is the same as m times v dot. Okay, so m times the sum of all forces is negative b times the speed, and this is m times v dot. We can take the Laplace transform, b times v of s equals to m times s v of s. And I forgot the force here, sorry, f of t, f of s. All right, so two forces, the force input and the viscous friction. And now we can do f of s equals to v of s ms plus b, and the speed over force is 1 over ms plus b. Are we good? And we have a mass of 1 and b is 0.1, so this gives a transfer function h of s as 1 over s plus 0.1. Okay.
Looks good.
Looks good. Okay. So you have 1 over s plus 0.1. And now we need to write this expression in the form of a constant divided by s over omega 0 plus 1. If you remember the standard form, this is our cutoff frequency right there. What do we have here? This would be the same as dividing everything by 0.1. Right, the top and the bottom. So we have h of s is the same as 10 divided by s over 0.1 plus 1. I have to divide the top and the bottom by 0.1. Okay. Any questions? You just need to prepare the transfer function in the format required for the Bode plot. Yeah?
Yeah, it looks good.
It's good. Okay. So here is a transfer function. So there's 10 on top here that I forgot. And now let's do the Bode plot. So let's just start. Let me just write the equations here. G of s equals to 10 over s plus 0.1. And let's try to do this. I might have to change these numbers, I think. No, it's not gonna fit in here. 10. Yeah, no, that's fine. Should be fine. Okay, so let's assume that this is our Bode plot. Let's take this frequency here. Well, because our cutoff frequency is 0. Sorry, this is 1. 1 second. This is 0. This is 1, 0.1. Because our cutoff frequency is 0.1, let's assume that this one here is 0.1, so 10 to the power of -1. This is 10 to the power of 0. This is 10 to the power of 1. This one back here is 10 to the power Which building blocks do we see?
We have a constant gain.
We have a constant gain 10, and we have a real pole. Real pole. So let's do them one at a time. Let's start with the real pole. The real pole is S plus 1, so S divided by 0.1 plus 1. The cutoff frequency of this pole is 0.1, is here. Right, it's this axis here. What happens? Up to the cutoff frequency, so anything below the cutoff frequency, what is the magnitude? What is the magnitude?
0.
0, exactly. 0. So anything below the cutoff frequency is 0. So here, go to 0. Okay. At the cutoff frequency, what is the magnitude? It's negative 3. Yeah, negative 3 dB. Now, what happens when you cross the cutoff frequency? We start to decrease by a factor of negative 20 decibels per decade. So at 10 to the power of negative 1, which is 0.1 radians per second, we are at negative 3. What happens when you reach 1 radians per second? When you reach 1 radians per second, well, this is a jump by 10. This needs to go down by 20. So what is the magnitude here?
Minus 20.
Minus 20?
dB.
3. Minus 23. It is minus 20. If you want to account for this negative 3 dB, it's negative 23. Now,
Sorry,
if you
can
keep
you oh, sorry. I was going to ask if you could explain the negative 3 decibels at 0, I guess, what that means.
Yeah. So this comes from here. So at the cutoff frequency, we are dealing with this expression. At the cutoff frequency, omega and omega 0 are the same. So we have negative 20 log of square root of 1 plus 1, which is negative 20 log of square root of 2, which is negative 3. Right, at the cutoff frequency, these two numbers here are the same.
Right, okay, thank you.
Okay, so if we are negative 3 and we went down by a factor of 10, we increase the frequency by 10, we go down by 20, we are negative 23. What is the magnitude at 10 radians per second?
Minus 43.
Minus 43, very good. Minus 4. Everybody can see that. This here is negative 43. Yeah. This
Yeah.
goes down. Right. Right. So a slope of negative 20 decibels per frequency decade past the cutoff frequency. What is missing? Well, there is a gain of 10. So you have 20 log of 10. Log of 10 is 1, so this is 20 dB. This 20 dB comes from this 10 on top here. So what happens here? What happens?
Everything's raised by 10?
Everything is raised by 20.
20, right.
20, right? 10 is in the non-frequency domain, in the frequency domain, sorry, in decibels, 10 decibels is, we are basically multiplying this curve by 10 in the non-frequency domain, or adding 20 decibels to sorry, let me put it this way. We are multiplying the curve by the equation by 10 in the non-decibel scale, or adding 20 decibels to the curve is the same statement, right? So everything now shifts upwards by 20. So instead of 0, we are at now 20. Instead of -3, we should be, this is a terrible drawing, at negative, well, not negative, we should be at 17. It's really hard to coordinate just looking at the screen like that. So this is now 17 dB. And now we start to go down. So -23 becomes -3. -43 becomes -23. Like that. Everything shifts upwards by 20 dB. And this is now the magnitude for that curve. What is the phase? Well, the phase is easy. We have the phase of a constant gain that we know is 0, so we don't even have to bother. And we have the phase of the pole at the origin, the real pole. And the phase of the real pole, we know that it's 0 up to the cutoff frequency. So from here to there. At the cutoff frequency, it is -45 degrees. And past the cutoff frequency, it shifts to 90 degrees, -90 degrees. So if we interpolate this, we should see something along these lines. Okay, and this is the phase of the entire transfer function. Any questions? No? Yeah, perhaps.
Can you explain why it goes to -90? Is that a property for the poles on real axes?
Yeah.
Oh, it is. Okay, right.
Yeah.
Sorry.
Yeah, this is what we saw here. All right.
Nice.
Past the cutoff frequency, we now have a frequency that is much greater than the cutoff frequency. So that term in the tangent tends to infinity. And the tangent, inverse tangent of that is -90 degrees.
Okay, thanks.
Any other questions? The silence kind of worries me a bit.
Makes sense.
Makes sense? Okay.
Do you mind going over how you got the phase one again? Sorry.
Yeah, so the phase I take it from here. So we are looking at 3 distinct phases. The first one, look at this equation here. The first one, the cutoff frequency is much greater, is much smaller. Sorry, the frequency is much smaller than the cutoff frequency, so this tends to 0. And when that happens, the result is 0. The second case, the cutoff frequency and the frequency are exactly the same, so we're dealing with the inverse tangent of -1, which is -45 degrees. And in the third case, now we passed the cutoff frequency, so this frequency is much greater than that. This number tends to -infinity, and this turns out to be -90 degrees.
Okay.
All right, I just want to erase this, and you're going to see one last building block. We won't have time to do an exercise, but I will post the solutions. And I have for Bode plots a bunch of videos already made. You can watch those for extra practice. And of course, if you want to do this in MATLAB, the command in MATLAB is simply Bode of G. G is your transfer function, and it should plot the Bode plot for you. So if you define a function g of s in MATLAB, then Bode G of S shows the Bode plot. You're welcome to use that to check your results. Okay, now let's look at the last building block for this lecture is the 0 on the real axis. So you'll notice here something very similar to what we had before, except that the negative sign is gone. The negative sign is gone from here and is gone from the tangent function. So we can conclude, and I'm not going to go through the entire derivation, but the only difference is that we had 1 over this for the pole. So this 1 is gone, which means the negative sign is gone in the log when you do the log property. And because of that, the magnitude now is positive log of this thing, is the opposite of the pole at the pole on the real axis. The only difference is now the slope will start to increase up to the cutoff frequencies is still 0. At the cutoff frequency, now have plus 3 decibels. Past the cutoff frequency, the slope goes up. The phase will follow a similar trend. Before the cutoff frequency, 0. At the cutoff frequency, now we go up, we go to plus 45 degrees. And past the cutoff frequency, plus 90 degrees. So the real 0 is exactly the negative of a real pole on the Bode plot. The same as we did before for poles and zeros at the origin, we can see the same trend here. They go up instead of going down. Here's a plot. We have 2 functions, 1 over S plus 5. And 1 over an S plus 5 simply. And you can see that they go up and down, right? Okay.
So here, Professor, one of them is pole and the other one is 0.
Yeah, so this is the 0. This is the pole.
Okay, thank you.
Yeah. Okay, and then look at the phase. Phase goes to plus 90 degrees and then minus 90 degrees.